Feel bad. Who am I to abuse you? So my name is Peter Hughes. I'm lead engineer at a company called Push Technology. We're kind of based in the UK, as you might tell from my accent, and also over here in the States. We kind of do real-time data distribution software, and recently branched out into cloud service too. And while we don't necessarily work directly in the kind of REST space, we definitely kind of cover a lot of the same problems of essentially making things on one side of the internet talk to things on the other side of the internet, which is kind of applicable here. In terms of my background, I started off as a normal web developer, hacking away in PHP of all things, and gradually moved over to working kind of in Java, JavaScript, Clojure. So I've kind of mostly spent my entire career focusing on this whole kind of internet-facing web application space. And that's my Twitter handle if you want to read my inane ramblings. So, what constitutes bad? In the context of a REST API, I'm kind of focusing on a couple of things here, right? So, poor usability. We provide APIs over the internet for people to use. They're not some single solitary thing that we keep in a silo. If people can't use them, or if even your end clients, even if you control them, are still having problems interacting, then that's bad. Insufficient scaling capacity is a really big problem, and this is essentially a case of you start off, maybe you're a startup, you're hacking together your first prototype app, you put it on the web, you release it, and suddenly it is all over Hacker News or Reddit, and what you thought was just going to be servicing a couple of hundred users is now servicing thousands. Those numbers add up. They make a difference. If you can't scale what you have, you're going to be looking at a world of pain just to get your product back to where you thought it was originally. And the other kind of flip side of this is inappropriate usage. REST is great. It doesn't solve every problem. You need to actually consider the problem domain that you're trying to solve, whether REST is really the most applicable solution for you, and what the alternatives are. Or at least consider this and then make an informed decision. So, kind of going off of usability to begin with. Design for failure. Errors always happen. Your code is never flawless. Your systems will always break eventually. You can't expect whatever you've written, even if it passes all of your unit tests, to actually hold up in a production environment forever without falling over eventually. There are so many variables involved that you just have to accept that errors always happen and handle them as if they are just as important as the normal usage pattern of your REST API. And REST is HTTP based, right? That's the whole point. HTTP already has a whole bunch of ways of communicating errors back. There's so many APIs that I've seen in the wild that return responses with a 200 OK header, regardless of whether everything is okay,
It's okay when you give the error back.
Precisely, yeah. And, a lot of the systems that are going to be consuming the responses from your REST API, they speak HTTP. They know what these response codes mean. Use them. You can communicate so much usefully. And this really, from a performance perspective, still has a knock-on effect. If your, clients, maybe it's not your clients that you've written, but you've exposed an API, some other guy comes along, writes a mobile application that's, hitting your service. If you throw an error somewhere and return them, a useless response, what are they going to do? They're either going to completely break the application or they're going to try again. And if they're trying again because they don't know what to do, you're just encouraging them to keep repeating the same mistakes. That isn't good for anyone. You know, if you get a blank response, I don't know whether my request has failed because I hit the wrong URL, because the service is actually down behind the scenes, because I haven't been authorized. There's so many potential ways for things to break. Tell your users what they've done wrong. A great example of something that does this right is Twitter. So on their developer page for the API, they list every single HTTP response that they will send you and tell you exactly what it means. And this is a good example to follow. So, errors are the bad case. The good case is, you know, what we're actually delivering over our APIs, which is data. And it's becoming pretty easy to say, right, let's go for the kitchen sink approach. You know, I have my client, be it web, mobile, whatever. I'm requesting a resource. I'm going to give them everything that they could possibly want over the wire. That can be a lot of data, especially if your system evolves. You may start off only returning a small response. As your data model changes, as your core application adds more functionality, and you start having to send more data over the wire, that's a hell of a lot of bytes that add up eventually. When you consider how many users you may be having, how many requests you're going to be servicing over a certain point of time, the more data you send, the more bandwidth that costs. And again, it may be fine for small numbers. You may be expecting only, you know, a couple of hundred people to be hitting your services over a large time frame. But if and when that changes, you now actually start needing to consider what the throughput of your network actually is. And of course, you know, the clear solution here, right, is to consider really what exactly is the bare minimum required. If you can get away with sending less, do it. It's, you know, good for you. It has less cost for you in terms of putting data over the network that you're presumably paying for. And it's good for the clients. If you're on mobile, you have a fixed data plan. If your client's constantly polling, the less data being used up is good. The problem that kind of crops up at times too as an illustration is we all generally have decided that JSON is a good format, right? It's a hell of a lot better than XML. No one's arguing that. But just consider some of the redundancy that actually comes into the way that we send stuff. So this is, you know, a not unreasonable example of the kind of payload you might expect, you know, to get from a response. We've got, you know, some UID, title, key, whatever, you know, just generally useful information for a simple resource. Now, assuming that this data has changed and the client then requests it again at some later point, the only data that's different from what the client received previously are those two strings. Everything else is exactly the same. You're sending redundant bytes over the wire. And again, it seems small, but if your payload increases in size, if you're doing this at really high volumes over a large period of time, that's a massive number of redundant bytes that you're just happily serializing over the wire over and over again. And this is obviously partly informed by your expected usage patterns. If you have a public API, though, you have no control over the usage patterns of your clients. And inevitably, this is what it looks like. Over and over again, it's a monkey with a miniature symbol just clapping its hands and sending off yet another fetch or post. And, you know, you can't control that. You can't control how many people are actually using your systems. When it's on the internet, it's free for all. And so you need to start asking yourself, well, what exactly is the number of requests that I'm servicing that don't change? Do I really need to blindly respond every single time? This goes back to the error thing, right? HTTP 304, content not modified. It's in the spec for HTTP that the user has requested something that hasn't changed. It's a really useful way of communicating that, hey, maybe slow down. And everything has a cost. Any aspect of your REST API will have a cost associated with it. You need to be cognizant of that, and you need to profile this. So as I kind of said, the number one thing is bandwidth, right? It's going over the internet. That's kind of a given. But you have other considerations here too. You have CPU and memory usage. Maybe you're fine for really simple operations, but if you had something that requires more complex, querying of databases, coordinating over multiple processes in your backend, and then resolving those to create a response, that all takes time. That all takes memory. And the more requests that you have within a short time frame, the more of your resources you're going to be using up. And you also have to look at the hardware limits here too. This is going over the internet. You're putting all your data through whatever network interface your host machine has, and that has a finite limit. If you're really talking about high-end loads, you could be saturating a 10 gigabit NIC, potentially, depending on how much data and how many clients you're servicing. And there's other really subtle things like the number of file descriptors that your OS allows you to have open, which are often used, for handling network requests. So these are all limiting factors that will hit you eventually at scale. You need to be cognizant of really what your costs are for every single aspect of your REST API, because if you get super popular, they're going to come bite you in the ass. Next thing is coupling, which is a TV show I'm guessing none of you have seen. So this is about really the back-end architecture. You kind of, can start off simple with a nice little toy prototype app, which is, you fired up your shiny new JavaScript framework that came out 2 hours ago, and, that's all well and good. You've set up your endpoints, everything's fine. When you're actually trying to do a real product, you have more components. You have your back-end databases. You have additional processing. Perhaps there are bits of the back-end logic that aren't written in the same language as what you're using to actually service the REST requests. So you have those components that need to be communicated with. More components means more bottlenecks. There's a law called Amdahl's law, which essentially says that the total throughput of a system cannot exceed that of the combination of all the components in it. This limits scaling completely. So the number one thing to avoid is a one-to-one mapping between cheap, such as actually servicing, a GET request, and the costly operations that actually involve these back-end systems. It's incredibly difficult to scale up when all of your logic is completely intertwined, and you can't separate out the bits that are just saying, hey, I've got an HTTP request, I'm going to send you a response, and oh shit, we now have to do image processing over this batch of 50 image files, right? You want to have these separated. You need to have clear delineations between responsibilities in your architecture. So, this is kind of a really naive example, but it's still one that tends to happen in so many cases where you have your incoming request, and through whatever logic is in your API, that directly relates to a query onto your database. Even if you may not be, you may be abstracting away this with libraries, and you have a nice, super performant querying, interface that lets you forget about the realities of what's actually going on under the hood when you hit your database. Ultimately, you may well still be inadvertently adding far more load onto your backend systems than you really think you are. And this really just is a bad system, because you're now having to wait on your fetch request for the database to perform its operations, whatever that is, to be pushed back through. Don't do it. The other kind of coupling problem is when you have, say, a REST API and a normal user-facing web application. And it's really tempting to say, hey, the back-end logic for both of these are essentially the same. It's doing the same thing. One's returning JSON, the other is returning HTML templates or whatever. But they're basically the same thing. So, let's cut down on the boilerplate. Let's write them into the same application, just using, different parts of the routing engine to separate them. Put them in the same process. All's well and good. Super easy, hack it out in a couple of days. That's great until one side of that equation gets put under far more load than the other. If you have your API and application running the same process, and suddenly your API is being hit by 100,000 requests a second, that's going to slow down everything, including your user-facing side, which should really be completely separate. You can't scale it when they're that closely entangled. What you're really doing is trying to ignore the fact that they're separate interfaces over the same back-end logic. Split it out. Don't do it. So, mitigation. And there aren't any silver bullets here, right? I'm not going to kind of recommend specific products or technologies to solve this, because it's so dependent on the problems that you may be encountering. It may be that you've already considered half of these things, right? But these are the general strategies that you want to be employing. Load balancers. Really super simple. You just stick them in front of your services. You can now have multiple instances, and you can instantly handle far more load than you're used to. That's really great, except they don't handle stateful things well. So if you have an authorization system, you now have to care a hell of a lot more about which clients are being routed to which service instance, and actually maintaining a stateful context for each session. That can also be expensive. Queues are super, super good for your backend architecture. So rather than having direct communication between separate processes, use a more message-oriented paradigm. Say, put a queue between, your API and your database. Let that handle the kind of throttling of excessive load. It removes the direct correlation between hitting one part of your service and hitting another part of your service. It gives you much more fine-grained control over handling back pressure, about rate limiting. It ultimately gives you a lot more of an asynchronous architecture, which, if you has anyone actually read the Reactive Manifesto or heard of it? Okay, a couple of people. So I highly encourage all of you to look up the Reactive Manifesto. It's basically a paper written by a couple of very intelligent people, far more clever than me, and it essentially describes the realities of working in high-scale, high throughput, reactive web applications and services, dealing with modern realities of handling hundreds of thousands or millions of clients or petabytes of data, and how do you maintain that same performance throughput? And a lot of that is based around taking a kind of event-driven model to your back-end architectures about actually splitting out the interactions into a way that can be more easily managed. There's other stuff you can do too, right? So you can trade consistency for responsiveness. I have that the other way around. Ignore me. So we tend to think that if you, request some data from, an API, it should be the same. And that's really, really a nice idea, one that doesn't necessarily work in the real world. If you have a large number of instances, probably spread around the world because you want to reduce latency from different geolocations, right? That's a distributed systems. And distributed systems are really fucking hard. The best way to accommodate this is to say, hey, maybe we won't have instantly updated data across the entirety of the service at any one time. You allow a certain degree of inconsistency there, a certain amount of stale data. What that allows you to do is scale far more easily. It allows you to say, hey, I can now spin up multiple instances, and sure, the data might be a minute or two old occasionally, but the benefit is that you no longer need to strictly coordinate your entire data model, wherever that's stored, across a large number of disparate services. You can do reverse proxy caching as a way of, like I was saying earlier, reducing the redundant data that you're sending to clients. Reverse proxies are great. The difficulty is in validating that cache. It's not, there's no easy solution. There's only least bad solutions from validating caches, because of course it's great to say to your clients, hey, this data hasn't changed. When that data does change, you need to inform both your cache and your users. So an easy or a workable solution for cache invalidation in this instance might be something like a timer. You cache stateless responses, you keep that response cached for a couple of minutes, and then subsequent responses go back through, hit your back end, get cached again. Yes, you're introducing stale data, potentially, but it does give you at least the possibility of knowing how stale that is, of having at least a degree of insight and control over what your clients are receiving, with the benefit of increasing performance and reducing workload on your actual back-end systems.
So I haven't done something like that before. Is it possible to give like an option on the user interface to invalidate that? Like, so it might work for UI, say, if you would like the up to the minute thing, hit this button and you'll do a server hit. Is it possible to do something like that?
Yeah, I mean, it's entirely up to you how you would configure your particular caching strategy. And it may be as simple as saying, hey, if the user has appended, a URL parameter that says, no cache, skip them straight through. It's up to you how you want to handle that degree. And it's a great point that maybe you'll have different tiers of clients, different usage patterns across maybe your websites and your mobile clients. You can use this kind of thing to account for that. Maybe on mobile, you want to cache more aggressively than for web clients.
I was just kind of asking
yeah.
this, have you used any platforms for it that kind of mitigate that issue? Like, the CloudFront has the 15-minute cache invalidation thing. Have you found that using those services just adds complexity, or?
So it's yet another thing that you have to configure and work with, right? So in that respect, yes, it increases complexity. But this is kind of the trade-off that you have to take. You add a small amount of complexity using stuff like CloudFront, or you could use, say, Nginx or something like that. A lot of these technologies you're probably already using in a web application anyway. It's a little bit of complexity, but the benefit is that it ultimately provides, an increase in responsiveness and performance.
Well, then some of the hard parts aren't your problem anymore. Like with CloudFront, you're betting that Amazon's engineers know how to handle that part of it better than you do.
Sure.
Probably appreciate that.
Exactly. I mean, this is the thing. Your primary focus in all of this is going to be whatever your application logic is, right? Doing all this kind of mitigation of all the problems that come from the internet, it's necessary, but it's also problems that are being solved by other people. And rather than trying to do it yourself, if there are solutions out there that work, do it. And so the other side of this is containers. Like I was saying about the coupling, you want to keep different parts of your services separate processes, maybe separate host machines. Containers are brilliant because, who here uses Docker? Yeah? So, it's a godsend, right? It makes it so easy to say, hey, this part of my service is getting hit really, really hard. I just want to spin up a couple more instances, do on Amazon, whatever, and rather than having to look at your tightly coupled system and go, oh, crap, I need to pull apart this bit of code, and, we can spin up a new instance, but now it's going to start interacting weirdly with everything in the back end. Keep your services separate, use containers, deployment becomes so much easier, and responding to increased demands for deployment. So, the internet. Yay. Oh, sorry?
I have one question on the last slide.
Sure.
Where do you see the role of e-tags in cache invalidation? And is that I know a lot of people don't like to use e-tags for some things, but is it more appropriate in the development of a REST API?
I think e-tags especially come down to who you think is actually going to be consuming your REST API. In terms of if you have full control over, what what requests are going to be sent, and you can control, the headers and tags over the being sent, then that's fine. You're going to get bad requests if, you're exposing this API to the public. People may not really respect whatever, system that you have in place. It ultimately depends whether you want to use them or not. I don't really have a great answer, I'm afraid, on that specific matter. So yeah, internet, which obviously looks exactly like this, as we all know. So, when you're not surfing on a keyboard over it, it has a few downsides. It's unknown, it's uncontrolled. You literally have no ability to state any claims about the quality of your internet connection. And it's going to let you down. There's going to be insufficient bandwidth, inconsistent bandwidth, which is possibly worse, because at least if it's insufficient, but consistently insufficient, then you know how to handle that. You're going to have high latency or varying latency, especially over mobile networks, where you're switching from Wi-Fi to 3G to 4G to, nothing, just because you're walking around, your house or your office. So latency, very variable. And these are all realities that you have to deal with when you're sending data over the internet. You can't get around it. This is kind of something that Push Technology, we've of course branded this as kind of internet sympathy, right? What you experience when you're developing locally on your machine and you're testing it over localhost is a complete lie. Localhost does not exist in the real world. And things will break in interesting ways precisely because of these limitations. You have to understand them, especially in mobile. So, REST over HTTP, the HTTP kind of behavior pattern is based on slow start. So it starts sending, packets and datagrams slowly, and then will ramp up exponentially until it can get to a point where, it's not getting any significant, pushback over the network. If you're mobile and you're dropping connections, it can happen fairly frequently or sporadically. This has a knock-on effect, and the knock-on effect is exemplified by the fact that you're using your phone's radio when you use the network. There's a paper I was reading where essentially for phones where the screen is turned off, the highest usage of the battery comes from network interfaces. That's just apps running in the background, firing up that cell phone radio constantly due to network usage, and that accounts for 70% of the draining of your user's battery. That's a lot. And we come full circle. If you're doing large payloads over the internet, which require the mobile connection to be on for a large amount of time because more bandwidth takes more time. It's a simple reality. You're doing periodic polling from a client. Again, that's just constant usage of your user's internet connection that is ultimately killing their battery. It's not good. So there are, of course, solutions. Avoid polling, which is a solution. It's probably not the one that you really want, though, for your chat application or something. I don't know if you saw the real-time internet talk earlier, but we're moving towards a world of reactive applications where we expect real-time data. If you're doing that over REST, the only way to achieve that is through constant polling. It adds more load to your back end, and it also kind of screws with mobile users. So you could do things like batching data. That's a pretty good solution. Instead of constantly polling, in order to account for the fact that data might be changed frequently on the server side, you poll less frequently, but then have the server deliver a batch of all the data that may have changed. The problem being that that is kind of starting to become not RESTful, right? The general nature of REST is that you have single endpoints that deliver known resources. Batching kind of messes with that because, unless you start adding in extra parameters to specify how large the batches are or the last, value that you received, you're adding a lot more kind of stateful nature to something that inherently should be stateless. The other alternative is single streams rather than multiple HTTP requests. And this is one of those things that is kind of becoming solved as we go through HTTP 2, where you have, multiple connections being multiplexed together. So potentially, as the web evolves, some of these problems will disappear. But there's a problem with these solutions. Like I say, they're not necessarily really in tune with REST philosophy. It's a bad fit. So, has anyone actually seen Wallace and Gromit?
Yeah.
Ah, hey, British culture. So that's the wrong fit. What's the right fit? REST solves particular problems for a particular environment. That isn't always the case for what your application is really trying to do. It's perhaps, the easiest, it's the most straightforward. A lot of our kind of web frameworks that are sitting around make it super easy to produce a web application that serves data over REST. But perhaps we should be looking at other solutions like streaming data, PubSub as a model instead of request response. Things like Meteor, Firebase, just to be a company shill. We have a great new service called React, which does exactly this, streaming data in real time over WebSockets. It comes down to the fact that what you really want is something that works. No one cares. Your users do not care how conceptually elegant your architecture and REST APIs are. They care that it works, that you have useful applications. And oftentimes, what that means is if you want to focus on performance, you have to make hacks, or you have to accept that perhaps you're not doing things necessarily in completely the right way. Maybe you're adding in degrees of state to your backend services in order to better, cache or batch up responses to your users. You have to make these kind of trade-offs. JSON. Everyone basically assumes that JSON is the only way of delivering REST data. It's not. REST is, at its core, delivering HTTP responses to requests. You can choose different formats if you want. As we kind of showed earlier with the payload, when data changes, you have so many redundant bytes that you're constantly sending. Maybe you could choose a binary format that reduces that, or an explicit schema in your responses that doesn't necessarily contain all of the keys for the values. We find, as I was kind of saying about the reactive manifesto, that event-driven, message-driven architectures prove themselves to be a lot more performant. It's kind of Node's whole shtick, right, is that it's event-driven, it's asynchronous, it's all really, really good and fast because of that. That isn't really the same as what HTTP provides, which is request response at its core. And you have to essentially say sometimes a service that has to block its response until stuff in the background has happened and the user can actually be told whether something has happened isn't the best fit. Sometimes you want to have an event-driven system. You fire off an event from the client to the server, and then at some point in the future, that client gets sent an event back saying, hey, this is the response. There's a lot of different ways of thinking about this that, depending on your application, depending on the requirements for the interactions, make REST not necessarily the best fit. So, this is a whole bunch of different problems and potential solutions. And ultimately, we want to make not bad things. You want to, ultimately, over all of this, the core message is consider your design. Consider the application, the API that you're building. Consider the format of the data, whether you need to have redundancies, whether you can minimize the amount of bandwidth usage. It's about knowing how this data is actually going to be used, how it's going to be consumed. Benchmarks and performance profiling are your friends here. You really, really, really want to know how your system performs under load. You want to see what breaks. You want to do, Netflix's chaos monkey approach of just throwing shit at it and then figuring out where your weak points are. Because if you just blindly assume that your local unit testing, your integration testing with a whole 5 users is informing you of the problems of your system, you're going to have a bad time when you put it on the internet. Services like Locust.io, Blitz.io are really useful for this. They're designed specifically to test REST APIs at high load. Do it. You'll be happy for it. And, instead of feeling bad, you'll end up like that. Right. Thank you. Whoop, 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 whoop. Any other questions or?
So I'm kind of interested in your WebSocket implementation. Now, is that within the API? How are you sort of tying that into your policy?
So, WebSockets are completely orthogonal to REST. Essentially, like I was saying, it's a different paradigm. It's a different way of using it. You have to have more complexity both on the client and the server side to really get the same level of ease of use that you can get through REST as it currently stands. But the benefit of that is that you now have a streaming channel. It's a long-lived, persistent connection. Changes to the data don't require any interaction from the client because you can just push it down the stream.
Do you have any idea how that impacts battery life on, say, mobile devices?
So the general feeling is that a single persistent connection tends to be more battery efficient than multiple sporadic requests.
You're transferring overall much less data.
Yeah, you're transferring less data, and also you're not, when you're doing periodic polling for the mobile battery, you're essentially kicking the network radio, going, hey, wake up, do this thing, okay, we're done, you can turn off. 30 seconds later, hey, wake up, do it again. And that constant, wake up, going asleep cycle is less sympathetic to, the performance.
There's a point where, doing these, if you're pulling at inconsistent enough rates versus a consistent WebSocket,
sure.
There's probably a balance point in there.
Yeah, exactly. And again, that's where, profiling comes in. It's so specific to the usage patterns of your service. But in general terms, for certain kinds of usage, WebSockets will be a preferable solution. Great. Oh.
Do you do profiling as well, kind of in terms of intranet traffic versus to the client traffic, in the sense that, like, it sounds like in your distributed model you have a middle tier and then kind of back-end APIs.
Mm-hmm.
Will you have the back-end APIs return the full payload and then the middle tier kind of strip it out, or how do you, or do you think it needs to go all the way back to the furthest back-end stuff?
So typically, when you have multiple tiers, the general design goal should be that at each stage, you're reducing the number of interactions down to the next tier. By reducing the number of interactions, you can kind of get away with having larger payloads from, the very furthest of your backend service being bubbled up. But it depends how you want to do that. I mean, you could have a distributed cache system like Memcache, Ishcache, whatever, that is kind of sitting and is accessed by both the front public-facing side and the back-end components, and using that as the communication channel. In which case, it may be that you're pushing data into that and then consuming or withdrawing only a small amount of that same data from the public-facing side. But it kind of relies on the amount of data you have, what you're really doing with it, what the production style of it is. If you're constantly changing it, or if it's more of a database, slow-moving data.
Have you seen any difference in performance as far as different serialization methods for your responses to your REST API? Let's say standard JSON versus binary JSON, or
So from what we've seen, this is so speaking more specifically in a streaming context, but the same principles really apply across all of this. We've found that within our product, Diffusion, when we use an explicit schema that essentially serializes down at the binary level and reduces, redundant keys and values being sent, we get up to 80% bandwidth reduction compared to services like Pusher or PubNub that are just sending straight up JSON. Protocol buffers are also really, really good at kind of compressing down the size of the data. Ultimately, binary is going to be more efficient. The trade-off is the cost of deserialization and also potentially the ease of use. If it's a completely closed internal system and performance is very critical, I'd absolutely recommend a binary serialization format. If this is something that you're going to be exposing as kind of like a public-facing thing, you have to consider the fact that a lot of people probably don't want to be deserializing binary.
Right. You have to maybe package a library with it for them to leverage.
Exactly. Yes.
Just one more layer.
Well, then you're dealing with people who go, wait, I gotta push what that reply now?
Right. Yeah.
Mm-hmm. Yeah. Right. Well, thanks very much.